So physics is basically trying to understand nature. So in general, when we talk about physics, we are basically talking about how nature works. So the key idea here is to deal with this works part of it, right? So how nature works, meaning that we got to find out what the natural laws are. We got to learn to apply the laws to solve the regular problems around us. Too often when we hear about physics, I don't know about you guys probably had the same experience as I did. Growing up, I grew up in the Apollo era. So for me physics basically meant lunar missions, various beautiful pictures of galaxies and nebulae and planets and satellites. So I got very attracted to all this fancy stuff that you can't necessarily kind of go out and touch. But physics is actually all around us, right? I mean, the fact that you are sitting on this table, the table is made of a certain material that's not cracking up. It has a certain timber to it, there's a certain acoustic propagation property. The fact that this won't conduct current, there's physics all around you. You can go to your playground and you'll be amazed at how complex the physics around you gets. So I'll try and link with some of these ideas as I go along. Not that it's a part of the syllabus, but because I think that's an integral part of learning the subject. But at the same time, it is very important to stay on track also. But at this point, I will just give you some basic ideas. So when we talk about how nature works, we really are talking about the tiniest particles. So something as small as the tiniest particles to something as large as the farthest reaches of the universe itself. Now, this is pretty astounding because I do not believe our human brains are necessarily capable of really understanding the entire range of physics. We try, we must, but it's very, very hard to do. So, for example, if you could take an atom, let's say I just pick up an atom, which of course I can't do quite so easily, but you can look at atoms in the lab. That is possible to do. So suppose you took an atom and you want to go inside the atom and take a look at the nucleus. This nucleus is something that we know a great deal about. Remember, the nuclear bomb went off a long time ago. That changed the world, right? We talk about nuclear catastrophe all the time now. So the nucleus is 10 to the minus 15 meters in size. So just to give you a sense of it, 1 meter is how much in feet? Come on. Give me a ballpark number. 3? Oh, that's about right. 1 meter is about 3 feet, right? So 1 meter is quite large. So a nucleus is 10 to the minus 15 meters. So that means 1 followed by how many zeros? Fifteen zeros. That's how small the nucleus is. And we know a great deal about the nucleus. We don't know everything about the nucleus, but we know a great deal about the nucleus. We worry about people getting nuclear weapons, right? So we know the physics at this scale. Isn't that amazing? And the fact that this was developed in the 1940s, late 1930s and 40s. So, but the smallest length scales that we can go to now is even smaller. And that's about 10 to the minus 18 meters. So the smallest would be 3 more zeros. That will get us to 10 to the minus 18 meters. And 10 to the minus 18 meters is when you begin to see stuff inside the nucleus, stuff that make up the nucleus. And these are the what? You guys know what this is? We left atoms a long time back. We went inside the atom, then we encountered the nucleus. We went inside the nucleus. Yeah, quarks. So these are new guys called quarks that hang out inside the nucleus that make the nucleus what it is, right? So these quarks are in that length scale. These quarks are about 10 to the minus 18 meters. And thus far, experimentally speaking, that is the smallest length scale about which we have some real information. We can actually determine whether they really exist or whether they're a figment of our imagination. And the answer is they really exist. We know that for a fact. Okay? So this is the stuff that people get Nobel Prizes for, obviously. But we know physics at this length scale. What happens at even smaller length scales, we don't know. There are theories about it, but we don't know. Does it matter? Yes, it matters. Why does it matter? Because the universe in which you live in now, the properties of this universe around you is probably determined by stuff going on at even smaller length scales. So just to understand the world in which we live, that is important. Okay, we can't ignore it. So this is where the smaller stuff is. Now, as far as the larger stuff is concerned, the universe is a very weird place. So the universe, as we know, is expanding. That's a known fact. We can measure universe's expansion very well. We have known it since the 1920s, I believe. But the fact is that the universe is expanding. What does it really mean? That's much harder to understand. So when we say the universe is really expanding, the very space on which we are standing, this space itself is bloating out. So it's a very intrinsic level expansion. The easiest analogy I can give you, if you were two-dimensional, and if you were living on the surface of a balloon, and if the balloon was blowing up, not exploding, I mean expanding, then that would be an analogy in two dimensions. Because the space in which you are sitting on top of the balloon is itself expanding. So here in 3 dimensions that's expanding. That's the expansion of the universe that we live with. Now of course, solar system, how much solar system is floating up? That's super tiny. But when you look at everything at the universe's length scale and time scale, it's a pretty good expansion. But let's forget about the expansion for now. If you were to figure out what is the farthest object that we can see from Earth, the answer that you will get is of the order of 10 to the power 26 meters. I don't believe your brain or my brain or any human brain is capable of really appreciating this number. But the number is in this ballpark. Not that we know it really well, but the universe's length scale is of the order of 10 to the power 26 meters. So in other words, the stuff that's that far out that we can still see essentially means that light from that object has hit our eyes now. And typically these objects were the earliest objects that actually formed in the baby universe. And we can see them. So as we look out farther and farther, we are actually looking back in time. Okay? So this is all fancy stuff. I'm not here to necessarily, unfortunately, entertain you with fancy stuff. I'd like to, but that's not my job. So what we do is actually the real work. The real work that we do involves 3 things. We make measurements. We make measurements of stuff around us. Okay. How big is something? How small is something? Blah blah blah. We try to explain what we see. And then, based upon what we have measured and explained, we try to predict how it might behave. So we make our measurements, we try to explain them, and then we try to predict how something will behave. This is where your problem solving comes in. So when you are doing problem solving, what you're really doing is you are actually doing the explanation and the prediction part. When you do the lab, which is not a part of this course, you do the measurement part. Of course, we'll try to make measurements in our head, but that's a little bit different. So to do measurements, you really need three things. You need to somehow be able to measure space. You need to somehow be able to measure time. And you need to be able to measure mass or matter here. So to measure space, it's very easy. To measure something in space, you basically measure length, area, volume, etc. So I will denote this as L. And normally, one writes it like that. So this is called the dimension of length. It's nothing to do with 1D, 2D, 3D. It's another use of the word dimension. It's called the dimension of length. The dimension of length, when I say dimension length, that means those square brackets are there and it has a length unit in both. For time, it's obvious. We'll use capital T for this, but normally for time, we only use the notation small t. Do not use capital T in general for denoting time. And for matter, we are talking mass. And that would have the dimension of mass like this. And there are many, many kinds of units, and we'll talk about different kinds of units. But the units that scientists generally use are the meter, kilogram, second units, MKS units, or also known as Sistema Internazionale, so that's SI units. So we use the MKS units or the SI units. So therefore, given MKS, for length we have meters, for time we have seconds, and for mass we have kilograms. There are other system of units. For example, in the US, we have somehow not moved over to the MKS units or SI units. We use feet, right? A foot or feet for length. We use seconds for time, and we use pounds for mass. Pound is a little confusing because there's something called pound, there's something called pound weight. But when I say pound, I will literally mean the mass. So we will do some conversions of units, and I'll take you through that a little bit later. But before I get to the boring details of conversion, I want to get on with some physics itself. So let's talk about explanations and predictions. So as far as the business of explaining and the business of predicting is done, we need one thing only, and that is we need equations. Equations help us connect a left side with the right side and gives us the power to make a quantitative description of something. So therefore equations are obviously very important. One of the things about equations is that the left side and the right side must have the same units. So I'll come back and harp on that, and I'll hold you up on this in quizzes as well. And I'm telling you ahead of time because this is a very powerful weapon that you need to develop skills with. The way you do physics correctly is by making sure you're good at catching your mistakes. We all make mistakes. I make a lot of mistakes. You will make a lot of mistakes. We all do. And the only way we would know how good we are is in how well we can catch our mistakes. So let us say we take a very simple problem. Actually, it's not a simple problem, but we'll pretend it's very simple. Let us draw a rocket. Rockets are usually not ones that you see in Earth. Usually you see them outside the Earth. That's where they end up. And they end up in an environment where gravity is what? Very tiny or zero, right? So when you are in space, inside a rocket, you can say that gravity is extremely weak. And for our practical purposes, for now, we can take it to be zero. How weak is weak? Just to give you an idea, it's about 1/1,000,000th of Earth gravity. So once you leave the Earth, the gravity that you will feel, it's not entirely zero, it's about 1/1,000,000th of Earth gravity, 10 to the minus 60, it's called microgravity. So if you look into NASA website, you will find plenty of stuff on microgravity, because NASA does a great deal of research on microgravity. So suppose you were lucky enough to be very wealthy, and suppose you have bought your ticket on the rocket, and there you are. And that would be just about the right way in which I would see you, right? Because there's no gravity. You will not be standing, you'll be floating. So, if I happen to be around you, I can push you. You may not like it, but I can push you. So suppose I give you a gentle push. I won't push you hard, because you will bang up against the wall. There's no gravity, there's almost no resistance. You won't be able to stop yourself. So what will happen is, if I give you a gentle push and stop, you will immediately start to float in the direction in which I have pushed you, right? So you will probably end up going in that direction. Let us suppose that you end up moving because of this push at some fixed speed v0. Whatever that number may be, it can be half a meter per second or whatever. Just imagine a number. v0 denotes that number. So you are moving with v0. If you are moving at v0, and suppose you are moving at v0 for an amount of time t, let's say t is few seconds. What does the product of v0 and t possibly give you? The distance you have traveled, right? If you are going from Buffalo to Rochester, you know darn well that you drive about 65 miles an hour on I-90, you get there in roughly an hour, right? So speed is 65 miles an hour, time is 1 hour, multiply 65 times 1, it's about 65 miles. That's roughly the distance between Buffalo and Rochester. So I can denote the left-hand side by a distance d. And this distance d would then be equal to v0 times t. That is my first equation. And one of the simplest equations that will invoke. Whenever you write an equation, I really want you to get into this terrible habit. You should be very unhappy. Why should you be unhappy? Because you don't know if you have done it right or wrong, right? So I want to make sure, before I'm excited about it, I want to make sure I got it right. So distance has the dimension of what? Distance has the dimension of? Huh? Come on. Don't be so afraid. I don't hurt anybody. Loud. Length. I was looking for the magic word length. Remember this? When I say dimension, I mean that. So this is L. T is obviously time, right? That's not rocket science, even though it's in a rocket. What about speed? L upon t, because we are traveling distance at given time. That's what v0 is. So now you see that I have done what I would call dimensional analysis of this equation. So this is a trick that you've got to pull every time you write an equation, just so that you know that you didn't screw it up, because if you don't, chances are you will. So you see, time cancels out because there is a numerator time and a denominator time. You're left with length, and the left side is length and the right side is length. Both dimensions are the same, so therefore there is a strong chance this equation is possibly correct. So I will call this equation 1, and because there is nothing special about this v, I can just get rid of the 0, make it just d equal to vt. So any equation is actually telling you a story. And one way of describing a story is to make a picture about it. So one way you make a picture about it, for example, is you can draw x and y axes. And in this case, your x-axis will be time. Normally, x-axis ends up being time in most things we will do. Not always, but most of the time. Because x-axis is the independent variable. And time is usually something that we can't really control. So time flows in its own way. So therefore, by default, most times, time is the x-axis variable. And let us say on the y-axis, I measure what distance I travel over time. So if I look into this equation, if I put t equal to 0, my d should be 0, the way it's stated. So if I'm describing this equation pictorially, at t equal to 0, d should be right here. That's very easy to do. Then I stick another value of t, that's at t equal to 1, I get some value of d that's based upon what's the value of v. So if I join these points, I'll end up getting some kind of a straight line. These are my data points, let's say. So the slope of this straight line can be measured, and the way I'll do it is I'll stand here, I'll drop a perpendicular, so this is a 90 degree. Maybe I'll stand there and I'll drop a perpendicular, that's a 90 degree. And then I'll stand here and drop a perpendicular here, that's 90 degrees. So the slope is defined as this length along the y-axis divided by this length along the x-axis. Okay? So in general, if I call this x-axis and if I call this y-axis, the slope would be change in y value for the corresponding change in x value. So in other words, I can take a value here, call it let's say d2. I can take a value here, call it d1. I can take this value here along x-axis, call it t2, and this one t1. So then I should be able to write that my slope, in this case slope will be v, would be d2 minus d1, which will give me delta y, divided by correspondingly, d2 is at t2 minus t1. You have to be careful about the order. If you mess up the order, then you'll get the wrong slope. So, as you can see, this is how you calculate a slope. So that speed v can actually be quantified based upon this picture I've drawn. So every equation, from time to time, I'll ask you to actually draw a picture of it, to construct a picture of it. Because then I'll give you problems that will be based upon the constructed picture and how to solve it. Okay? Are you guys with me so far? Anybody lost me? Anybody getting bored? Should I speed up? No. Right. I'm trying not to speed up too much. All right. So there is one more thing that I want to say. You see this equation. I just drew one picture of this equation in which I took d and t. But I can make another very important picture of this equation, and that would be that I can write t along the x-axis like before, but I can put the speed along the y-axis. And let us say, for argument's sake, that the speed is fixed. Speed doesn't vary. So if the speed is fixed, then this would be just like that, right? And then ultimately at some point I stop measuring. So now you see, I have another description of this very same equation with other variables. I use the t variable, but instead of using the d variable on the y-axis, I use the v variable on the y-axis. But even this makes a lot of sense, because this area is what? What is the, how would you mathematically express that area? How do you measure an area? Okay, I won't ask you because you have already answered once. Huh? Louder. I still can't hear you. Raise your hand first. So, yeah. You are a very soft-spoken person. So what? No. You are going too far ahead from me. Yeah.
Multiply the time velocity.
Yes. So area is basic. If you have A and B as two sides, area is the product of A and B. So in this case, what we'll have is D equals to Vt. See, that's exactly what we have here. So this area here is this time, is this V and this T. So therefore Vt. And indeed, this area therefore is the physical significance in this depiction. And that physical significance is actually time. Okay? It's distance. So Vt is equal to D. So that's another way of writing the same thing. Now, suppose that it turns out that your speed is not uniform. Suppose after I pushed you, you started kicking and screaming. So if that's what you did, then chances are that your speed might actually fluctuate, because if you'll be moving your hands and your feet, that might have an effect on the speed that you acquire because of my mean push. So now you see, if I plot T versus V, if your speed is not uniform, your speed might go up or fluctuate. What am I going to do then? How will I measure how much distance you have moved? Now your speed is no longer fixed. You see, there's a way to cheat. And the way you cheat this is you say that while this may be hard to measure, I want to measure V bar. V bar, this bar means average speed. Okay, average speed. Because while your speed may not be fixed, you certainly can calculate an average speed. How would you do that? Well, there are many ways of doing that. A simple way may be you make measurements at various points in time. Let's say this is V1, this is V2, 3, 4, 5, V6, etc. Then it turns out that your V bar, okay, is going to be the number of V's that you have. So V1 plus V2, whatever, divided by, let's say, N. And N is the number of measurements you have done. And those are the numbers you got. So if I want to write it as a summation, I would say each of them I'd give it a generic name I. So I equal to 1 to N, V sub I, which is like this, divided by N. Or I can take the N outside and make it look even prettier. I can just say 1 over N here, because the N is not inside. But that means the same thing. What I wrote there is the same thing as I wrote in longhand. So therefore the more general formula is D equals V bar T, and I would hence call it equation 1 star for now. The first one was equation 1. So before I proceed further, let me go back and tell you a little bit about units. I told you already that units matter, and we'll be dealing with various kinds of units. Now, this meter, kilogram, second, or foot, pound, second, these units are not always convenient. For example, you want to measure the size of a bed bug. If you want to measure the size of a bed bug, how big is a bed bug? Anybody checked out a bed bug? No? It's about I think it's about 2 millimeters, maybe even less, 0.2 millimeters. It's very tiny. So the natural unit to measure the size of a bedbug would be millimeter, probably less than a millimeter. If you have a foot or if you have a meter, then you'll end up with a whole bunch of zeros before you get the number. And the reason why those zeros show up is because you have chosen a unit that is very large. Okay? So therefore, while these may be the fundamental units, meter, second, kilogram, foot, pound, second, foot, second, pound, whatever, we often work with derived units. For instance, we might be working with units that are suitable for a given problem. So for example, let's say we are talking about speed of a turtle. Now, while turtles are great, turtles are not exactly known for moving very fast, right? So let us say that a turtle moves at 5 meters in 1 hour. I don't know, I'm just making up this number. So the speed of the turtle in these mixed units is 5 meters per hour. Now, this is not a very good unit, so I'm going to play around with it. Or maybe this is a very good unit. I can try and see what happens if I try to write it in meters. Well, we invent some trouble because meters per second. So for example, I would be writing 5 meters, but 1 hour is 60 minutes, right? And then 60 seconds is 1 minute. So therefore, if I write 1 hour in seconds, this would be 60 seconds per minute times 60 minutes per hour. So therefore, it will be 3600 seconds. Observe how I wrote. This is how I expect you to write. When you do unit conversions, that's the expectation. You don't write it that way, I take off points, okay? So this is the only way I can force you to not make an error. So 5 meters in 1 hour can be written as 5 meters in 3600 seconds. So this would be in meters per second. This is the speed of the turtle. Now if you carry this out, I'm not worrying about significant numbers, significant figures yet. I'll get a number at 0.0014 meters per second. Naturally, this is not a very convenient number. There's too many zeros we are carrying. And that's basically because we are using meters per second, which in this case turns out to be a very large, to be not quite the appropriate unit for the turtle, because the turtle moves very slowly, so second turns out to be too refined, and it doesn't really help us very much. So I can now change things around, and I can say that, 10 to the 3 millimeters is equal to 1 meter. So if I multiply it with 1,000, I can get a number where the total speed would be 1.4 millimeter per second. So that may be a more appropriate number. So what I'm trying to tell you is that we oftentimes could be doing unit conversions like this. In fact, the first homework that you'll encounter will take you through a great many unit conversions. And then I will be holding you up for the unit conversions as we go through the later homework and as we get into the exams. So for example, we are talking about the size of a helium atom. So helium is the second guy. The lightest one is hydrogen. After hydrogen, helium formed with an extra proton. So a helium atom is 10 to the minus 11 meters in size. So this is basically equal to 0.01 nanometers, because a nanometer is 10 to the minus 9 meters. Nanometer is, nano means minus 9, 10 to the minus 9 meters. So 0.01 times 10 to the minus 9 meters makes it 10 to the minus 11 meters. Or a similar unit that also works well would be 0.1 angstrom. So you see, these are the derived units we deal with. An angstrom is 10 to the minus 10 meters. So we work with derived units quite a bit. I'm sorry, is this causing a problem? Is that better? So for example, let's do a very simple conversion before we run out of time. Let's go from 60 miles an hour, which may be a speed you are familiar with if you are driving, 2 meters per second. So the way it works is that 1 mile is 1.609 kilometers. Again, I'm not paying attention to significant figures now. I will pay a lot of attention to that soon, but not today. If I want to care about significant figures, I would have to write 1.000 miles is equal to 1.609 kilometers. I'm not writing. So 60 miles, if you do the multiplication, would be 60 miles times 1.609 kilometer per mile. Okay? And 1 hour, we already know, 1 hour is 3600 seconds. So if you do the division, 60 miles per hour is going to be 60 times 1.609 divided by 3600, and this comes out roughly to 27 meters per second. Now that's a lot. That's 51 feet a second, by the way. So 60 miles per hour we know is a large speed. It's actually very hard for us, I find, to gauge our speed as we see in the car to conceptually what we are used to, because 60 miles per hour is something that we often drive at. But 60 miles per hour is 51 feet per second. It's 81 feet per second, 27 meters per second. So it's a very large number. All right, we are pretty much out of time. We'll pick up a little bit more speed on Thursday and see you then.